Let's keep the party rolling with example number 6 on the mean value theorem and the first derivative test. Again, we have a function and we're supposed to identify increase, decrease, max, min. So once again, it all involves the behavior of the derivative. We start out by taking that derivative. Now, wouldn't we want to do a little rewrite on this? In the interest of space, I'm going to do it this way, but wouldn't that be x plus 9x to the negative 1? Let's use those negative exponents to our advantage. And therefore, the derivative of that particular function would be, I'm doing this, wouldn't that be 1 minus 9x to the negative 2 power, otherwise known as 1 minus 9 over x squared. So again, we use those negative exponents to make the derivative easier, and then in this case it would make sense to me to rewrite it back. So there's our derivative, 1 minus 9 over x squared. And as mentioned earlier, there's two types of critical values we need to investigate. The first would be to set that derivative in its entirety equal to 0 and solve. We're looking for horizontal tangent lines. Remember, lines with the horizontal lines have a slope of 0. This is just algebra. Let's see, how about we clear the fractions by multiplying both sides by x squared and distribute the x squared, which would give us x squared minus 9 equals 0. Add 9 to both sides and take a square root. Now, remember square roots produce plus and minus. It's very easy to overlook that plus or minus. All right, so there's two numbers on the x-axis where the tangent lines are going to be horizontal when we ultimately graph this. So that would be important to notice. All right, now, this is a little different than what we've seen before. It's easy to overlook the undefined aspect of a derivative. Yes, this derivative contains a fraction, and specifically that x squared on the bottom of that fraction, if that x squared equals 0, then we would have division by 0. That's undefined. Square root, so x would equal plus or minus 0. Haha, 0. All right? So anyway, that's an important thing to note here, that we do indeed have a value in this case where that derivative is undefined. And we'll talk about what that indicates when we get deeper into the graph here. All right, so there you have them. We have plus and minus 3 would be places where the derivative was 0, and we have 0 where it was undefined. I need to erase that now. So again, take that down, pause, do whatever you need to do. So plus and minus 3 and 0. All right, I guess I can leave them up for a little bit. Sorry folks, this is really cramped quarters here. I feel like a caged lion as far as board space is concerned, so I'm doing the best I can. So again, I'm putting those three values, those three critical values on this number line, and later on I'm going to put our graph over here. All right, now it's imperative that we label the fact that the derivative is 0, recall, at the negative 3 and the positive 3, but at 0, it's undefined. I'm writing UND, or you can write a U there for undefined. But these labels are up here are, how is that first derivative behaving? That's why this is called the first derivative test. All right? So now, we will put numbers into the first derivative. Notice this says f prime of a number. I'm going to pick negative 10 for that region, and we're putting it in that derivative. So that would be 1 minus 9 over negative 10 squared. Negative 10 squared is positive 100. So 1 minus 9 100ths, that would be a positive number. So I'm just going to indicate that that's positive. And out here, these tangent lines all have positive slopes. Again, apologies for the cramped quarters of the board here. Let's get that out of the way and make that a little bit bigger. All right, so the first derivative is positive in that interval, which indicates increase, right? Okay, so let's go ahead and put that here. From negative infinity to negative 3, this graph is going to increase. Let's identify that. That's part of what the paper grader will be looking for, all right? Then we'll do f prime of a number in between here. I would suggest Negative 1, that lives in there between negative 3 and 0. We're putting it in the derivative. That's why it's called the first derivative test. Testing numbers in the first derivative. 1 minus 9 over, let's see, negative 1 squared would be positive 1. That's 1 minus 9. That's going to be negative 8. Negative 8. You can write negative 8 on your paper if you want. I don't care. The main thing is you realize that when you stick that in there, that derivative is negative in that interval, which again indicates a decreasing behavior. So from negative 3 to 0, this graph shall decrease. All right. Now we'll do the same thing with a number in here between 0 and 3. I hope one of these black markers works better. Put it in the derivative. 1 minus 9 over 1 squared. That's 1, right? And that would be negative 8. That'd be negative, okay? Notice these things don't necessarily alternate. That's why we need to test each region. We have no idea what the pattern will be. How about from 0 to 3, decreasing? 0 to 3. This graph decreases. All right, and then f prime of 10, a number out here bigger than 3, in the derivative, 1 minus 9 over 10 squared is 100. That would be 1 minus 9 1/100ths. That will be a positive number, and so that first derivative has positive behavior in that region. What's a first derivative? Slopes of tangent lines. That's why I'm drawing these lines with positive and negative slopes in each of these regions. How about from 3 to infinity? This graph will increase. See, I'm putting these in the increase-decrease boxes. All right, so that takes care of that. And then it's on to the matter of maximums and minimums. This is where we go locate points that we'll plot on our ultimate graph and see if they're maximums and minimums. So, I need to make space here now. Feel free to pause at any time. I'm sure you wish you could do that during class. All right, now the number negative 3. Now remember, here we're looking for points. That means we're going to put these in the function, aren't we? So, negative 3 plus 9 over negative 3. That would be negative 3 minus 3. Looks like that's negative 6. That's an ordered pair. That's going to be on our graph here in a minute. I can only do one thing at a time. And look at the behavior of the derivative. Increase coming in, decrease going out. I would suggest to you that therefore, that ordered pair, negative 3, negative 6, that's a point. These are intervals. These are points. It's going to be a max, right? Let's see. How about 0? If we put 0 in the function, we have 0 plus 9 over 0. Oh, did I just say over 0? Oh, no, you can't do that. Right, so that's why the derivative was undefined there, because the function is undefined at 0. All right? But why is that? We've talked about this many times. A number that causes division by 0 is either a whole or an asymptote. Since this won't cancel out, that's an asymptote. So the point is, there's an asymptote at that. And we'll reflect that on our graph. So just keep in mind, there'll be an asymptote, a vertical asymptote at 0 when we graph it. The function is undefined there, which made the derivative undefined there. All right, so that's important. And then 3, all right, we put 3 into the function. 3 plus 9 over 3, that'd be 3 plus 3, that'd be 6, that'd be 6. That's an ordered pair, we're going to plot it. And look at the derivative. Decrease coming in, increase going out. Minimum. So we'll identify that the ordered pair of 3, 6 shall be a minimum on this graph that we're about to enjoy building together here now. So I'm going to put some scale over here, some XY coordinate system. See, all this graph paper would have been already on the board normally, but we can only do so much. All right. And my camera crew went on strike, so, you know, I could do the graph way over there and have them pan, but, you know, anyway, this is a one-man show today. Okay, so it looks to me like the scale, I'd probably scale the x-axis, x scale. I'm going to go by ones, all right, because the relevant numbers are -3, 0, and 3 on that x-axis, right? Looking at the values of y, 6, -6. I would also say that a scale of 1 on the y-axis seems logical. So I'll identify that. Please, I ask you to identify the scale that you're using on these different graphs. And here's 1, 2, 3, 4, 5, 6. And here's 1, 2, 3, 4, 5, -6. Those values of y that we found when we found these points. So let's plot them. So we've got the ordered pair -3, -6. And let's start graphing this. I kind of work left to right when I look at that first derivative test number line there. So increase, hit that point, decrease. So between that point and the asymptote, it's decreasing, isn't it? So we've talked about this before. I'm going to get that scale label out of the way now. But how about we increase to that point? We have a horizontal tangent line. Oh, and we might as well put our asymptote in there, right? We've identified there's an asymptote at 0. I don't know if you can see that very well, but here at 0, I put this dotted line. And isn't this graph then, between that point and the asymptote, decreasing? So it's going forever down there, isn't it? In the hot place. Okay, I have comments I can make, but I won't. All right. And then the ordered pair 3, 6. 3, 6. That's one of the few times my filter worked and I didn't say anything. All right, what's going on? Between the asymptote and that point, decrease, hit the point, bounce back up. So what's this doing? It's starting up here at the good place, coming down, hitting that point, horizontal tangent line, bouncing back up. All right, so there would be your graph of that particular one. And you can quit watching now, but if I were you, you might want to continue watching if you feel like, I don't know, being infotained. But sorry, I didn't have my microphone on. You know, folks, I know times like this can be kind of tough, and I'm just here to give you a little bit of a pep talk. So, you know, I just want to remind you that it's really important at times like this that we don't stop believing. And if you're a mathematician, not only do you don't stop believing, but you don't stop deriving. Hope you enjoy. Just a small town nerd living in a dorky world. She took the XY plane almost everywhere. Just a city geek, born and raised in North Topeka. He took the XY plane almost everywhere. Teacher in a hokey room, students whine in sleepy gloom. For a while they can share the pie. It goes on and on and on and on. Math nerds plotting up and down the marker board. Their graph goes curving out of sight. Living just to find solutions, dividing somewhere in the night. my skills. Calculus is such a thrill. Praying everything to be precise. Just one more prime. Some will grin, some will snooze. Some are born to stay confused. The number E never ends. It goes on and on and on and on. Math nerds plotting up and down the marker board. Their graph goes curving out of sight. Uptight people living just to find solutions, dividing somewhere in the night. Don't stop deriving. Hold on to that proving. Uptight people. Don't stop deriving. Hold on. Uptight people. Don't stop deriving. Hold on to that proving. Uptight people. Don't stop deriving. Hold on to that proving. Uptight people. Don't stop deriving, and don't stop believing. We can do this.